In this video, we'll look at some of the key specifications of CMOS comparators and how to measure them. So some of the key comparator specifications include offset. Much the same way an amplifier has offset, a comparator can have offset, which will cause its output polarity to depend not only on the sign of the input, but perhaps on the sign of the input compared to some offset. Again, as was the case in amplifiers, that offset can arise because of systematic imbalances in the comparator's design, or simply because of random mismatches in the constituent devices. Another key specification of comparators that we'll look at is hysteresis, and then it's power supply sensitivity. The sensitivity of a comparator to the input is a key specification when it's being used to resolve very small input voltages, as well as its input referred noise, another key specification when using a comparator to resolve very small differential inputs. And then finally, the energy consumed per comparison is a power consumption metric that is very useful for dynamic comparators in particular. So let's begin with offset. Essentially, offset will arise if there's any mismatch between the two half circuits of the comparator. So the strong arm comparator is shown here as an example. Clearly, the circuit is intended to be symmetric here. There's the same number of transistor connections on both sides. Corresponding transistors in each half circuit should be sized identically, and good layout techniques used to try to match all parasitics at all of these internal nodes. But inevitably, that's impossible. Systematic sources of offset could arise if, for example, the wiring that's used to make any of these connections are different on the left half circuit and the right half circuit. You might think this is easily avoided, but in many cases it's not. In fact, it may be inevitable. You've simply got to cross wires over one another, and usually in doing so, it can be impossible to make all the parasitics perfectly matched. So any imbalance of that type will give rise to offset. And then you've just got random mismatches that arise because any pair of transistors considered here will have differences in threshold voltage, differences in transconductance, parameters, just because of random variations during manufacturing. So how do these mismatches result in comparator offset? Well, let's remember the operation of our dynamic comparator. Remember that we've got a regenerative core where two node voltages, Vx and Vy, sort of feed each other through these transconductors here. Now, this is going to cause a sort of I think of it as a race. So let's say Vx and Vy are both starting up at high voltages, as they would be in the example circuit shown on the top right here. Once the dynamic comparator is activated, both those nodes start getting pulled down low, but one of them gets pulled down low faster, and so it's sort of race to the bottom. At some point, one will have a head start that's just will have an advantage that's just insurmountable because the positive feedback will take over and then regenerate the voltage is something like this. But imagine that in this race to the bottom, one side is handicapped. So for example, that race is occurring because these load capacitors CL1 and CL2 are being discharged. What if one of those capacitors was a little larger than the other? Well, then obviously it would be discharged more slowly, all else being equal. And so that's going to give the other side an advantage in a race to the bottom. Another possibility is that the transconductors, GM1, GM2, may not be the same. Again, this can arise because of many kinds of mismatches in the schematic above. Again, the larger GM will have an advantage in the race to the bottom. And finally, any small signal resistances that show up in each half circuit will also create difference in time constants between these two nodes that can give one side an advantage in the race. Um, a final source of mismatch or imbalance that can give rise to offset that's identified here are offset currents that may be flowing either due to leakage through transistors that are off that may be mismatched in the two half circuits, or in some cases, offset currents are intentionally introduced into the latch in order to create an offset or to cancel an offset and try to make the overall comparator offset closer to zero. So mismatches in any of these parameters in the two half circuits can give rise to offset. Now the offset of the latch, as is the case with amplifiers, is quantified by the amount of differential input that needs to be applied to sort of overcome the inherent offset of the latch and and make the latch output very close to zero. That is to give rise to a situation where the two latch outputs, Vx and Vy, and the equivalent small signal schematic on the bottom right, both go down at exactly the same rate. Okay, and this condition is called metastability, and we'll talk a bit more about that later. So there's, regardless of what mismatches arise in the latch, there's some magic differential input voltage that will not be zero in the presence of offset that will cause this metastable condition to arise. And that value of input, that magic value of input that makes that happen is the input referred offset of the latch. And that's how we quantify latch offset. So how can we measure or observe the offset of a latch? Well, one simple way to do it is to apply very small differential inputs and clock the latch, starting it at a perfectly reset state so that there's no imbalance at the start of the simulation. And with a small differential input, if you wait long enough, eventually that you would expect the output should regenerate to the polarity of the input, even if it's very, very small. But what you'll find is that's not quite the case because of various sources of offset in the latch. And you could repeat this experiment for while changing the small differential input voltage. You could do a simple sweep, or you could do a sort of a search pattern where you basically look for the differential input that gives rise to the simulation result where the output looks metastable. That is, it takes a very, very long time, if ever, for the output to actually resolve one way or the other. It just sort of sits there at its reset level because at this magic input value, the latch is perfectly balanced. And once you find that magic input value, that is the input referred offset of the latch. Now, in the absence of any random mismatch in the transistor parameters of the comparator, you just need to do this sweep or search once, and that is the input that will give you the input referred offset of the latch due to systematic imbalances in the circuit. So you would see that, for example, if you did a layout of the transistors in the circuit, and again, there's some tiny imbalance in the parasitic capacitances associated with the layout, then you could do a simulation on that extracted version of that layout, and you would see any systematic offset that arises in the latch. But in many cases, especially for well-designed layout, you would expect random variations to actually be larger. To see random variations, you have to do a Monte Carlo simulation where you allow all of the individual transistor parameters in the latch to vary randomly according to the manufacturing tolerances in the particular process technology you're using. So you'd have to repeat this sort of sweep or search many, many times for many, many Monte Carlo trials. And as you do so, you may find different values of the imperfect offset of the latch. Sometimes you may find the offset is minus 2 millivolts, sometimes plus 1 millivolt, and you would have to repeat this trial many, many times and create a histogram of offsets that are observed. And so here's an example set of results that you might get. This is actually taking from measurement results of a real CMOS comparator and 90 nanometer CMOS a long time ago. This CMOS actually had a lot of offset on it, but that's good for the purposes of illustration because it's very clear. You can see that if you run the trials often enough, in this case, many copies of the same comparator were measured, but in simulation, you would form this histogram by repeating the search for many different Monte Carlo trials. So that would be many different combinations of threshold voltage variations in the transistors and so on. And you see in this case, okay, 30 times the offset was minus 40 millivolts, about 10 times the offset was minus 80 millivolts, and so on. And when you take enough trials, you can fit a Gaussian distribution to the results. And we expect the results to be sort of Gaussian distributed because most random variations in transistor parameters are Gaussian distributed. And then what you would find is that if there's a non-zero mean to that distribution of offsets, that is arising because of systematic sources of offset. So in this case, there's I would say there's minus 40 millivolts of systematic offset in the design of comparator. Again, that can be because of layout imbalances um, or something like that. And superimposed on that, you've got um, random offsets giving rise to the Gaussian distribution here. So the standard deviation of that Gaussian distribution in this case was about 26 millivolts, and that's caused by random mismatch. So, by distinguishing between systematic and random offset in this way, you can have a clue as to what the underlying causes of the offset are, and perhaps how to revisit your design if you need to lessen that offset. So, for example, if you want to lessen the systematic offset, you've really got to tackle systematic imbalances in the circuit or its layout. If you want to tackle the random offset, tighten up this distribution, then you need to just look at the transistor sizes. We know that many sources of random mismatch will be smaller if we use larger device sizes. Um, so that's why we need to distinguish between those two sources. I mentioned this earlier, but an alternative strategy to try to design the latch to have very low offset is to provide a facility whereby the transistor's offset can be trimmed. So here's an example of a latch um, where the clock signal is applied to the voltages V latch here, and activating these transistors pulls up the regenerative comparator's internal nodes up to VDD, and then when the latch goes high, these reset transistors are turned off, and these transistors down here are turned on, activating the back-to-back inverters, and that are driven by the input transistors Q3 and Q6, sort of initiating the regeneration phase. But you'll see in parallel with the input transistors Q3 and Q6, we have an additional transistor pair, Q4 and 5, that if driven by differential voltage at Vref here, can apply a sort of offsetting current into the regenerative inverter pair up here. So you can imagine, even if the input differential voltage is 0, if there's a differential input Vref applied, that's going to give one side of the regenerative comparator a bit of an advantage in the race to the bottom. So the sort of advantage imputed by Vref here can be used to cancel out any inherent offset in the latch itself due to systematic or random variations in the offset in the latch. So this is one way, a common way that offset compensation can be performed, is to provide an additional transistor pair with a voltage that can be adjusted to trim the offset and try to make it closer to 0. Another way to do this is to have capacitances connected to internal nodes that can be turned on and off by connecting the capacitors to ground or leaving them floating using switches. Okay, and by changing the load capacitance on each half circuit, as we've seen, that's another way to introduce offset into a latch. And so that's another mechanism that can be used to adjust latch offset and trim it closer to zero, perform offset compensation. Now, hysteresis is a phenomenon that's easily mistaken for offset, but is a little different. It arises due to a kind of memory in the latch. In general, a latch may have a preference to stay in the same state as it was on the last clock cycle. In some cases, the latch may actually have a preference for toggling, that is, for settling to the opposite state of what it was in the previous clock cycle. That's a little less common. But in either case, we call the phenomenon hysteresis because it represents a kind of memory in the latch. Ideally, we'd like a latch to depend only on the current value of the differential input voltage, but because of hysteresis, that's not quite the case. One common source of hysteresis in regenerative comparators is imperfect reset of the latch. So you may remember that when the latch goes into reset phase, one half of the differential output is likely already high. Let's say it's V out plus, whereas the other half of the differential output may be down at ground, and so when it enters the reset phase, some pull-up transistors are generally activated to pull it back up to VDD. Now imagine that those pull-up transistors are not fast enough, not strong enough, not delivering current to those nodes quickly enough to fully recharge them all the way back up to VDD. And this can also arise if the time allocated for the reset phase is insufficient. So in such a situation, V out minus in this case would not perfectly reach VDD before the next regeneration phase starts. So that's going to give V out minus an inherent head start, if you like, in the race to the bottom, uh, as we've been calling it. Which means that all else being equal, it's much more likely that the next decision will also be low. That is to say, even if the differential input is zero, the next output will certainly be low. Or sorry, I should say V out minus will be low, V out plus will be high again, because of this hysteresis, this kind of memory from the last decision. So how can we observe this hysteresis? Before you can do anything about a problem in a design, you need to be able to observe it. One way to do this is to clock the comparator repeatedly. So apply an alternating clock signal here, and to apply a slow but steady ramp in the differential input applied to the latch. Now, it's important to apply clock signal at your frequency of interest because clearly hysteresis, the amount of hysteresis in a latch is going to depend on how much time there is for reset of the latch. If you allow a very long time to reset the latch, then you're likely to see very little hysteresis. But if you're clocking the latch very fast, you're going to see more hysteresis. So apply a clock that's at your frequency of interest, and then apply a very, very slow ramp so that for one clock cycle, maybe you see a differential input of minus 1 volt, the next clock cycle minus 0.9 millivolts, and then minus 0.8 millivolts, and so on, right? So a really slow ramp. And what you will see is that, if the ramp is an increasing ramp, so sliding left to right along this plot here, Vn is gradually increasing, it may take a significant positive voltage before the latch's hysteresis is overcome and the output of the latch actually flips from logic low to a logic high. Then repeat the experiment with a downward ramp, that is, ramp the differential input voltage back down again. And in this case, what you may find is that it takes a different voltage to trip the latch in the opposite direction from high to low. In the picture shown here, it takes actually a negative voltage to trip the latch from high to low. So the difference between the trip point on the way up and the trip point on the way down is due to hysteresis in the latch, and the difference between those two trip points is sort of quantification of that hysteresis. Now you may notice that the trip points are not necessarily symmetrically arranged around 0 volts. Again, that somewhat expected because we know that the latch is likely to have some systematic offset here. Finally, I just mentioned that if your comparator includes an RS latch, I think it's important to include the RS latch in your simulation because the RS latch is also another source of memory in the circuit. And as we saw in our discussion of RS latches, um, you need a certain amplitude arising at the input to the RS latch before its inherent memory can be overcome. So you may see the effects of memory in the RS latch when you do this hysteresis um, test. Now, having found the offset of a latch, we can model it the same way we do in amplifiers. The input-referred offset of a latch can be kind of modeled as a voltage connected in series with the differential input to the latch, and then having modeled the input-referred offset in this way, we can consider the rest of the latch as being sort of ideal offset free. Now, an important point here is there's no reason to think that that offset will be independent of the supply voltage. In fact, it's quite likely that depending on how high the supply voltage is, the input-referred offset may change. And you can actually see this in your simulations. You can repeat your offset tests at different supply voltage level, and it's quite likely you'll get a different result. What does that mean? That means that um, if the supply voltage of a comparator is bouncing around, it's like having a noisy voltage source connected in series with the input because the offset will be also bouncing around. So this is one way to think about the supply sensitivity of a comparator. In general, as the supply voltage of a comparator bounces around, its decisions may change. So this can be quantified as an input-referred supply noise, um, and it's a sort of a measure of the power supply rejection of a comparator. Next, let's talk about the sensitivity of a latch. Now, if you do some of the slow input ramps tests that we described for comparators so far, you may find that when the input is around this magic voltage where it's right around the trip point of the comparator, it may take a very, very long time for regeneration to occur. So the black waveforms shown here are the typical ones that we see at the differential nodes at the regenerative comparator output, where one side kind of has an advantage, it's growing quicker than the other one, and then regeneration takes over, and then finally the latch saturates at the logic levels. But again, for this magic uh, sort of input voltage, you may see both sides of the regenerative comparator rise in unison, and that even when the positive feedback takes over, it's sort of a battle of equals. The two inverters are fighting each other and nobody's winning. And so this condition is called metastability of the latch. The latch is obviously very sensitive in this state. It may trip in either direction, but um, you only have a finite amount of time typically for regeneration. Before long, the comparator will re-enter reset, and if it does so before the regenerative comparator resolves a decision, then really the latch hasn't made a proper decision uh, there. And that's what will occur if the differential input voltage is too small or too close to its inherent offset, let's say. Um, so there's a sort of a minimum differential input that's required away from its offset value before before the latch can resolve. And that minimum differential input is called the sensitivity of the latch. Um, Now, clearly the sensitivity of the latch depends on how long you have to wait. Even very, very small differential inputs of a microvolt or a nanovolt, especially in simulation with no noise, will eventually resolve if you wait long enough. If the latch is perfectly reset and you wait long enough, eventually the positive feedback will take over. But so sensitivity should always be measured and reported with reference to a specific clock frequency. At that clock frequency, you only have a certain amount of time for the latch to regenerate. And if the latch hasn't regenerated by then, well, then, we say that the latch was metastable there. Now, a tricky point is exactly how much does the latch have to resolve before we say that, it's no longer metastable. Let's look at the black waveforms and let's say this is the end of our regenerative phase, clock phase, and the outputs have reached this level. Has the latch successfully regenerated? Well, what if we had a clock cycle that was a little bit slower and we wait till here? At this point, has the latch regenerated? Um, how are we to say? Well, one way is to simply define something. Say, well, as long as the logic levels have reached 90% and 10% of their full logic values levels, then we say that the latch is regenerated. That's one way, is to simply make a definition. But another way is to, that's perhaps more practical, is if you have an RS latch here, then really what you care about is have these logic levels, have these voltage levels at the output of the dynamic comparator gotten large enough to trip the output of the RS latch. So you can just look at these output voltages here. If they toggle, then we've waited long enough and the output was large enough and it was not metastable. If those output voltages don't toggle, well, then the differential input was still too small, and we haven't reached the sensitivity level of the overall comparator yet. Now, all of the preceding discussion about comparator performance has neglected the impact of thermal and other noise sources. Noise can be very important in a comparator when it's used to resolve very small differential input signals. However, rigorous noise analysis of a comparator is quite difficult. As you know, the noise model of transistors depends on their bias point, and because the nodes in a comparator are experiencing wide voltage excursions, the bias points of all the transistors involved are constantly changing. So it's difficult to understand what precisely the noise impact of each transistor is. There are lots of good papers on the topic, and they continue to come out, in fact. But we're going to instead just focus our attention on quantifying noise in a comparator and knowing how to measure it in simulation. Now, in order to be able to observe noise in a comparator simulation, you'll want to be sure that all the transistor models include noise. I use a transient noise analysis typically to do this, and you'll need to apply a relatively small input voltage. So this can be done by simply placing a small differential input here and applying a clock signal that triggers the comparator. Now, in order to prevent other effects such as hysteresis and the finite sensitivity of the amplifier and so on from impacting this noise analysis, I suggest just doing a single clock cycle so that you can initialize the operating point of the comparator in perfectly balanced state. There's no hysteresis, and simply apply a very small differential input, apply one clock cycle, and in the presence of thermal noise in the transistors, see which way the output resolves. Now you would expect um, the output to resolve, a binary value with the polarity of the input, but we know that won't quite occur. That won't occur because of the offset of the comparator. But on top of that, now we have noise. So the noise can cause the output polarity to be the opposite value of what you would expect, even considering offset. And it will do that with some probability. That depends on the amount of noise in the comparator which depends on the transistor sizes and bias currents flowing and so on, and it will depend on the value of the input voltage applied. So you'll have to repeat the simulation for each value of small differential input many, many times. And you'll see, for example, with Vin equal to, let's say, 3 millivolts, you may see that the output is binary 1 50% of the time and a binary 0 50% of the time, repeating this simulation maybe 100 times or more. So that would tell you one point on this plot of input voltage versus the probability of high output voltage. Now you can repeat the simulation another, let's say, 100 times with a different value of differential input. Let's say you apply a value of just a lift value from these results here. You apply an input of about 4.3 millivolts, perform another 100 simulations of a single clock cycle, and this time you find that the output's high 90% of the time and low 10% of the time. In fact, there will be some finite percentage here of simulations that may result in metastable output, by the way. But in any case, you form this plot, right? Applying a bunch of different differential inputs. And you'll see, first of all, that the plot is probably not centered around 0 millivolt differential input. This, again, is another way of observing the offset. It's not the quickest way to observe the offset because clearly here you'll have to perform many, many simulations to get this plot, and transient noise simulations, for example, are longer simulations than transient simulations without noise. But nevertheless, you'll see the input referred offset here as the point where the output has a 50% chance of being high and a 50% chance of being low. And using the other points, you can fit to it a Gaussian distribution. That's what's done with the black line. You shouldn't expect the fit to be as good as I've sketched out here. And naturally, there'll be some outliers unless you perform a huge number of simulations. But in any case, you perform a best fit, and then the standard deviation of that fit Gaussian distribution is the comparator's input referred RMS noise. Finally, you'll be interested in metric that quantifies the power consumption of a comparator. And since the dynamic comparators we've been talking about consume predominantly dynamic power dissipation, a useful metric for comparing comparators' power consumption is the energy they consume per comparison. So measuring power consumption is fairly straightforward. You have a DC power supply supplying a current IDD to the comparator, and you clock it repeatedly. And what you can expect to see if you look at the current waveform here is obviously not going to be a steady DC current. It's, in fact, there'll be periods of time where there's probably little or no current flowing in a dynamic comparator. There may be some finite current always flowing if, for example, you have a simple resistively loaded differential pair as the preamplifier. But there will certainly be spikes of current that arise when the regenerative comparator is activating, for example. So you're likely to see a current waveform that looks something like this, periodic with the periodicity of the clock. And then, so you can get that average current and then multiply that by the supply voltage here, and you get the average power consumption of the comparator. Now, one expects there to be two components of the power consumption. One, as we talked about, maybe a static power consumption, sort of baseline current that's always being drawn here. And that, again, may be due to any bias currents flowing, especially in preamplification stages. There may be leakage current, and perhaps there's some bias circuitry that's required. The rest of the power consumption will be dynamic power consumption, which, like all dynamic power consumption, should be proportional to the clock frequency and the supply voltage squared. And the constant of proportionality we can define as the effective capacitance, C effective. That's effectively the capacitance that is on average being toggled in each clock cycle. Finally, we find our normalized energy per conversion by dividing this total average power consumption P by the clock frequency. So notice that if you plot power versus clock frequency, let's say for a few different clock frequencies, you're likely to get plot something like this. Okay, and if we draw a line through them, we should be able to draw a pretty straight line through them, where the intersection of that with clock frequency of 0, that's not really probably a practical simulation we can run, but that's an indication of the static power. It's the power we would be burning even if we weren't clocking the comparator. And then the rest here, that's the dynamic power consumption. So the slope of this is our C effective VDD squared. So knowing VDD, we can kind of find our effective capacitance. So if the static power consumption is very, very small, okay, then we would find that the energy per conversion is given approximately by the C effective times VDD squared, and is therefore a constant across all clock frequencies. So we can use this energy per conversion step to kind of estimate the power consumption at any clock frequency. Again, assuming the static power consumption is small. If the static power consumption is large, you'll want to know that as well and add it to the dynamic part of the power here. A final point to make here is that if you're interested in the worst case power consumption, that is the most power consumption that the comparator can consume, you'll want to apply a small differential input during this test. Or in the very, very worst case, let's say a differential input that makes the comparator right around its metastable point. So if there's any offset, the real worst case will be applying an input voltage that is right around that offset voltage so that the comparator is metastable. And the reason is that while the regenerative comparator is regenerating, it's usually consuming more current from the power supply. Those inverters are fighting each other. All the transistors are probably in active mode, and so they're consuming power flowing directly from VDD down to ground, not being used to charge or discharge any nodes during that window of time. So that's going to give rise to effectively higher spikes in current here and longer lasting spikes in current. So the energy per comparison does depend on the differential inputs applied. That's an important point. And the worst case is small differential inputs.